If you take a skipping rope and fix it at one end, you can form harmonic patterns. You move the skipping rope up and down rhythmically, and you'll see the long curve of the first harmonic emerge. The distance from you to the other end of the skipping rope is half of the wavelength of the fundamental frequency. The first harmonic is one entire wave on one length of string or section of medium. We only see half a wave at the first harmonic, because one half of the wave is going forward and the other half of the wave is going backwards. They interfere with each other to generate the standing wave pattern. The wavelength of the first harmonic is twice the length of the string, lambda equals 2L, or L equals half lambda. Each subsequent harmonic is formed by driving the waves to higher frequencies. To do this on a skipping rope, you move your arm up and down quicker until a new pattern emerges. You are trying to achieve two complete waves on one string. This means that you have to oscillate the skipping rope twice as fast as the fundamental frequency. The frequency of the second harmonic is twice that of the first harmonic. F1 equals twice F0. Once you have achieved two complete waves on one string, you will see a pattern which looks like one wave. This is because you have one wave going forward and one backward to make one stationary wave. It is at this point that we can describe some aspects of the stationary wave. What looks like a peak in your stationary wave is in fact called an antinode. This is where the two travelling waves interact to form a peak. The wave and its reflection are actually antiphase to each other, but because one is a reflection, their amplitudes are in the same direction. Here we have a situation where a peak and a trough directly adjacent to each other are interfering to create a peak. The trough that is in front of the moving wave has hit the boundary, changed amplitude direction, and continued backwards. This does not happen with two separate waves travelling in opposite directions, only with a wave and its reflection. The point on your standing wave, where the wave appears to be at its equilibrium position, is called the node. It is where the wave and the reflection have cancelled each other out. A simple way of remembering these names is that a node is no. A node is a point with no amplitude, so it is no. The antinode is the other one. As we continue to increase the frequency of the drive oscillation, we start to see more and more standing patterns. Each one has another wave more than the previous one on the string. The first harmonic has one wave on the string, so the length of the string is equal to half a wavelength. One wavelength equals two string lengths. The frequency of the first harmonic is called the fundamental frequency and is given a symbol F0. The next harmonic has two waves on the string, so the length of the string equals one wavelength. The wavelength equals one string length. The frequency of this standing wave is twice that of the fundamental frequency, and so we can say that F1 equals twice F0. The next standing wave has three waves on it. The length of string has 1.5 waves on it, or 3/2 wavelengths. The wavelength of the wave is 2/3 of the length of the string. The frequency of the wave of 3 times that of the fundamental frequency. These patterns give us an opportunity to develop an equation linking the wavelength of the length of the string, the frequencies to the fundamental frequency, and the number of waves on the string to the string length. The frequency of any harmonic wave is the wave number multiplied by the fundamental frequency. The wave number can be determined from looking at the pattern of the standing waves. For example, the fourth harmonic appears to have two complete waves on it. The number of waves on a length of string is a little trickier. The fundamental harmonic has half a wave on the string. The next harmonic has one wave, or 2/2. The next one, 1.5, or 3/2. The next 4/2, etc. The number of waves on a string is equal to the harmonic number divided by 2. This makes it easier to give an equation for wavelength. Wavelength is the length of the string divided by the number of waves on that string. So, the first harmonic has half a wave on the string, so the wavelength is one length of the string divided by a half. This equals twice the length of the string. The second harmonic has one wave on the string, so the wavelength is one length of a string divided by one wave. The wavelength is the length of one string. The next harmonic contains 3/2 waves on the string, so the wavelength is 2/3 length of string. Next harmonic has 4/2 waves on it, so 2/4 wavelengths.